Hello students. In this module, we have to discuss about support vector machine. Let's have a look about learning objective. First of all, we can start with the support vector machine as an introduction. Once we get an introduction about the support vector machine, that's after that we can take it some mathematical aspects related to the support vector machine. Once mathematical completed, then we can go with the SVM, hard margin and soft margin classification. Once hard margin and soft margin classification should be done, then we go with the regularization. After regularization, we can see about some non-linear support vector machine classification things with the different type of kernel tricks, and at the end we can discuss about how kernel work with the support vector machine. Let's start with the introduction of support vector machine. So here, a support vector machine was first introduced in the 1960s and later improvised in the 1990s. It is supervised learning machine classification algorithm that has become extremely popular nowadays owing to its extremely efficient results. And support vector machine is implemented in a slightly different way than other machine learning algorithms. It is capable of performing classification, regression, and outlier detection. Support vector machine is a discriminative classifier that is formally designed by a separative hyperplanes, and it is a representation of example as point in space that are mapped so that the points of different categories are separated by a gap as wide as possible. In addition to this, support vector machine can also perform nonlinear classification. Let's take a look about at how support vector machine should work. Support vector machine classification algorithm used to assign data to various classes, and they involve detecting hyperplanes which segregate data into the classes. Support vector machine are very versatile and also capable of performing linear and nonlinear classification, regression, and outlier detection that we already discussed about that. Once idle hyperplanes are discovered, new data points can be easily classified. The optimization objective is to find the maximum margin hyperplane that is the farthest from the closest point into the two classes. So these points are called as the support vector that is already determined in this diagram. In the given figure, the middle line represents the hyperplane. So from the middle line, we are able to classify what data are positive and what data are the negative is there. The main objective of a support vector machine is to segregate the given data in the best possible way. When the segregation is done, the distance between the nearest point is known as the margin. So the approach is to select a hyperplane with the maximum possible margin between the support vectors in the given data sets. To select a maximum hyperplanes in the given sets, the support vector machine follows some particular type of the set, like generate the hyperplanes, which segregates the classes in the best possible way, as well as select the right hyperplane with the maximum segregation from the either nearest data point. So that's how support vector machine basically should work. Now, from the next session, we have to discuss about how support vector machine should work in terms of the mathematically. In this session, we have to talk about how mathematically we are working with the support vector machine. So the hyperplanes with the larger margins have lower generalization error. So higher margin or the maximum margin, it's a good condition because at the same time we are not getting any type of the generalization error. So it should fit it as an regularization. So the positive and the negative hyperplane are represent look like W0 plus W transpose X of positive. So whenever we are getting some positive samples, it represent within 1. And whenever the things are related to the negative, we are getting something based upon minus 1. So the same information are already provided over here. The classification of any input sample X test, it is work look like if W0 plus W transpose into X positive or X test is greater than 1. So those values are greater than 1. Those sample of X test is said to be in the class towards the right of the positive hyperplane, and those are considered as a minus 1 that should consider from the towards the left of the negative hyperplane. So right hyperplane and left hyperplane should work as a positive hyperplane and the negative hyperplane. So that's how it should work. But when you subtract the two equation, you will get this one. So which two equation? When you subtract W0 plus W transpose, X positive and X negative, this equation, if you subtract, you are getting X positive minus X negative is equals to 2. So see, here again, we are getting some lots of mathematical equation, but during the practical, we are not writing any type of the equation because we are having the scikit-learn library. So based upon that, we are doing everything. Length of vector W is considered as L2 norm of length. So W is equals to summation j is equals to 1 to m. Again, we have to provide W square of j. So at the same time, we are getting idea over here. And once you normalize with the length of WT0, arrive at this W transpose of X positive minus X negative, and magnitude of weight, it's W. So W will represent the magnitude of weight. Okay. So, and also we are also having some biases as well as. So B will represent the bias, but W will represent the weight over here. So 2 by W, so that should work over here. After taking about the knowledge related to the mathematical, next thing what we have to discuss, that is the hard margin classification and the soft margin classification. It is again an important part is there. So the left side of equation for the support vector machine 1 is given above, can be interpreted as the distance between the positive and negative hyperplanes, and in other words, it is the margin can be maximized. So what are the hard margin? Whenever the positive hyperplane, like a from the hyperplane, positive samples and negative samples are having large distance. Okay, so if they are having large distance, it is called as a hard margin. But if it is margin is not hard, margin is just a little bit okay, but how you can maximize that margin? So for that, you have to take an 2 divided by magnitude of weight. So at the same time, it's try to maximize that margin with the constraint that the samples are classified correctly, which is represented like that one, like W0 plus W transpose X, W transpose X of I greater than or equal to 1 if Y of I is equals to 1. And also 1 and minus 1 are again working over here, and this means that you are minimizing the magnitude of weight. So for minimizing magnitude of weight, you have to go like that one. Still in the same thing, this also means that all positive samples are on one side of the positive hyperplane and all negative samples are on the other side of the negative hyperplane, and this can be written consistently like as what here mentioned. If you want to minimizing magnitude of weight is the same as minimizing the one half weight square. So this figure is better as it consider differentiable even at W is equals to 0. And the approach listed above is called as hard margin linear support vector classifier. So that's how hard margin classifier should be worked in a support vector machine. After hard margin, let's talk about how soft margin classification should be worked. To allow for the linear constraint to be relaxed for the non-linearly separable data, a slack variable, so that is a theta, that is a one notation is there, so that can notate the slack variable. And so for that we have to introduce a slack variable, and slack variable measures how much input instance is allowed to violate this margin. So see, whenever the hard margin is there, so that is okay. So that is look like a linearly separable. But whenever we are getting some soft margin, like near the hyperplane or near the hypothesis, if we are getting any type of the sample, so those sample we have to provide to that sample to the slack variable. So slack variable is simply added to linear constraint. So after adding the slack variable, the not those vectors are related to the hyperplane that should go away, and subject to above constraint to the new objective to be minimized becomes. So that's how it should work over the soft margin classification. Again, same thing is there, like how to maximize the margin and how to minimize the margin. Like you have two conflicting objectives are there, like minimizing the slack variable to reduce the margin violation, and minimizing one half W square to increase the margin as well as. And the pi and the hyper parameter C allows us to define the trade-off as well as. And large values of C correspond to large error penalties, whereas smaller values of C allow for higher misclassification errors and the large margins as well as. So that's how we are getting an idea like how it should work over there. Okay, so once you can get idea about that one, so from the next session we can also discuss about like how we can apply the regularization in the support vector machine, so we can get idea about support vector machine with the regularization. In this session, we have to discuss about SVM regularization. So the concept of C is a reverse of regularization, and higher C means lower regularization. So whenever we are getting the value of C is higher, so it means regularization is not coming properly. And when the C value is lower, so it means regularization is higher. So similarly, which increase the bias and lowers the variance causing to the overfitting. So if you can see over here, the left hand side image, at the same time, the red samples and green sample both are very nearly to the hyperplane. So at the same time, large value of C. So we are not getting proper regularization over that. But if you can see the small value for C, so at the same time, we are having some hard margin or large margin. So maximum margin, you can also consider that one. So at the same time, the value of C should be small, but the regularization, it should looks very good. Let's see something based upon iris dataset. So the iris dataset contains the measurement of 150 iris flowers from three different species: Setosa, versicolor, and the Virginica. So here we are having three color, and based upon these three colors, so here we are just only these three color. These three classes is there. It's not color, but it's classes is there. So based upon these three classes, we have to create one type of the decision boundary based upon a support vector machine. So each row represent one sample. So flower measurement in centimeter are stored as a columns. So these are called as features. So we already know like sepal length, sepal width, petal length, and petal width are the features, as well as class label is targeted as a Y, but these four targeted as a input X. So that's how we are getting an idea. But if we have to do make some model based upon a support vector machine over here, so we can make it like this one. So from scikit-learn.svm import SVC. SVC stand for the support vector classifier. Here we are going with the linear classification. Okay, support vector machine should work for the linear model as well as non-linear model. When you want to go with the non-linear model, you have to use some kernel trick or kernel SVM. But whenever we are going with the things, whenever we are going with the things like a particularly linear thing, so at the same time, what we have to do, we have to go with the kernel of linear thing. So after applying linear classification with the linear kernel, then we have to fit it X train and Y train together, and then we have to find some decision boundary, and then we have to take an X label, Y label, and lesion, and then we have to show everything together. So that's how iris with that iris dataset we are getting SVM. This is just for your information. That's why I just taken very fastly regarding to this one, for because you are getting an idea like how it should goes with the support vector machine in linear way. Because also we have to see like how it should work within non-linear way. So let's start it with how we can find out same thing in a non-linear classification. So that is a non-linear support vector machine classification. In some cases, hyperplane cannot be very efficient. In those cases, the support vector machine uses a kernel trick to transform the input into a higher dimensional space. With this, it becomes easier to segregate the points. Let us take a look at this SVM kernel after, but first of all, we have to discuss some basic thing related to that one. There are two ways to solve the nonlinear support vector machine, either by adding polynomial features or by adding similarity of the features. So the polynomial features can be added to the data set. In some cases, this can be create linearly separable data set as well as. If you can see over here, so that is the left hand side we are getting just as an overview of things. But if this same thing we have to convert it into the two dimension or the three dimension, so we are getting this type of thing. And also we are able to draw the particularly inversely bell curve. So throughout the inversely bell curve, through this red line, we are creating one hyperplane. So that hyperplane can separate the blue samples and the green samples. So that type of thing we are able to do over here. So in this figure on the left, there is just only one and feature x1 is there, but in right, whenever we are trying to convert into the two dimension or three dimension, we are getting this type of stuff. And if you add x2 is equals to x1 of 2, so the data becomes linearly separable. So that type of difference we are able to generate over here in this particular nonlinear support vector machine classification. So in a support vector machine or the nonlinear support vector machine classification, we can also get in polynomial kernel. So polynomial kernel, that is one of the important approach from the nonlinear SVM side. So in a scikit-learn, one can use a pipeline class for creating polynomial features. So the classification results for the moons data set are shown in this particular figure. So here we are getting one of the like waves or type of shape is there, but that shape is nothing but it's coming from the polynomial kernel, and polynomial kernel depends upon the number of degrees. So degree can depends upon that one. So due to the degree, we are getting this type of output over here. So for a large dimensional data set, adding too many polynomial feature can slow down the model. Okay, so if we are having large of data set is there, and if I can provide the lot a degree like degree to 10, so it's not work properly because it's try to coming as a overfitting, so it's not proper. So you can apply kernel trick with the effect of polynomial features without actually adding them. And the code shown below trains an SVM classifier using a thread 3-degree polynomial kernel, but with a kernel trick. So here, if you can see on a first diagram, so it looks proper. But whenever we have taken d is equals to 10, so the difference or the shape is totally different, and it's also trying to overfitting. So that is not I want during the nonlinear SVM. So that is again important thing is that. So after that, let's talk about some of the more thing about polynomial kernel. As a just equation, the coding is there. Like whenever we have to take in with linear, like linear kernel is there. So here we are able to take kernel is equals to polynomial. So throughout this type of polynomial kernel, we are getting an idea like how it should work. So the hyperparameter coefficient of theta controls the influence of high degree polynomials. That how it should work over there. After that, the next topic related to that in non-linear part, that is a kernel SVM, and it's very very important part is that because an support vector machine kernel basically adds more dimension to a low dimension space to make it easier to segregate the data. So here we have to convert the things from low dimension to high dimension, and once we are getting from high dimension, and at the level of high dimension we have to create hyperplane, and again high dimension to we have to convert into the low dimension. So we have to provide the power, and again we have to do square root to get some proper solution. So it converts the inseparable problem to separable problem by adding more dimension using the kernel trick. A support vector machine is implemented in practice by a kernel, and the kernel tricks helps to make a more accurate classifier. Let's take a look about the different type of kernel in the support vector machine. So the kernel SVMs are used for the classification of nonlinear data. We already talked about the polynomial kernel, but now we introduce like how properly kernel SVM, because just only not a polynomial kernel is there, Gaussian kernel is there, then also quadratic kernel, cubic kernel, lots of kernel is there based upon like powers of things are there. So in this chart of this particular image, nonlinear data is projected into the higher dimensional space via the mapping function. So theta, it's represent with the mapping function. If you can see in this diagram, we are just only having this data points is there. With these data points we have to convert into the three dimension we have to provide the hyperplane. Once we can provide the hyperplane, again we are getting this type of things, so where it becomes like linearly separable, how it should work over there. In the higher dimension, whenever we are getting some three dimension is there, so in a higher dimension a linearly separating hyperplane can be derived, and it is used for classification. Because hyperplane, what is the actual work of hyperplane? The actual work of hyperplane, that is the classification. So a reverse projection of the higher dimension back to the original feature space take it back to nonlinear shape, and that's how it should work over there. Also, if you can get some more idea about like how it should goes when it's combined. See, if you can see over here again, it's representing two dimension. If I should convert this image into the three dimension, so I'm able to classify this thing. If I can convert into third three dimension, but in two dimension it looks very difficult to classify. But in three dimension it looks easy to classify. So we are getting four type of classes over there. So that's how we are doing the same thing over there. So as mentioned previously, support vector machine can be kernelized to solve the nonlinear classification problem, and that is the just coding for that one, like how this is just only code like how to implement these data points, just only that one. Otherwise it is not much related to the nonlinear SVM. This is just how to you how with the help of which code you can plot this type of points over there. Okay, otherwise after you are getting this one, based upon that you can also provide the kernel approach, and you are getting some proper solution over there. So it is again use the kernel trick to classify. Yes, so this is this one. So once we are getting this one, and again based upon this we have to we are providing any type of the kernel trick over here, and after applying kernel trick we I'm getting this type of binary classification. But it is not depends upon the logistic regression, it is depends upon the kernel support vector machine. And if you can see over here, kernel is equals to RBF. So meaning of RBF is a radial bias function. So radial bias function is nothing but a Gaussian function is there. So that's why there is a multiple mathematical function are working over here. So at the same time, whenever we have to take an RBF function, we have to use some gamma value, C value. But when we are going with the polynomial kernel, we have to find out some degree value, like degree is equals to 1, 2, 3, whatever the degree you can take, that is depends upon you. But that you have to take in that one. So after discussion about all the things related to the support vector machine in terms of linear classification and non-linear classification, let's end it with all the things with the machine learning application or the use cases. Basically machine learning in the particularly in the machine learning support vector machine, it's working as an advanced level of the logistic regression. When we want some beginner level of application, we are using logistic regression, but we want, whenever we want some advanced level application, so after next level of logistic regression, that is a support vector machine is there. So in the support vector machine, we can use face detection is there, text and hypertext categorization is there, classification of images is there, bioinformatics is there, protein fold and remote homology detection is there, handwriting recognition, generalized predictive control is there. So many more task is there. It's not look like just only one or two tasks is there. Also, there is a many tasks is there. Let's talk about some of the advantage and the disadvantage of the SVM. So first we can start with the advantage. So effective in high dimensional spaces, also still effective in cases where the number of dimension is greater than the number of samples. Okay, like we have to work with the 2 dimension to 3 dimension, and again from 3 dimension to 2 dimension we have to come. It uses a subset of training points in the decision function that makes it memory efficient, and a different kernel function can be specified for the decision function that also make it versatile. So this all task is very important related to the advantage of SVM. Let's talk about some of the disadvantage of SVM. So if the number of features is much larger than the number of sample features is larger than the sample. Like we are having 10 samples, but the feature are like parameters are having 20, 30 parameters is there. That's why. And avoid the overfitting in choosing kernel functions, and regularization term is crucial. So the support vector machine do not directly provide the probability estimates, and these are calculated using five-fold cross validation. So there is a depends upon multiple type of dimension is there, and we are not able to provide the probability estimates. So that's why we can go with the five-fold, like k is equals to 5 cross validation. We can go with like that one. So that is depends upon the data set part of that. Okay, so basically the whole the SVM module or the session is completed over here, and we discuss everything related to linear and non-linearity in terms of kernel, as well as the further things we can learn in particular practical session of the SVM. In this session, we have to learn about a support vector machine practical things. During the theory part of the support vector machine, we already discussed about a linear classification and non-linear classification. Basically, in this problem or in these practical things, we have to go with the social network advertisement data set, and that is work as a linear classification. But also with that, similarly we can also try the non-linear approach over here. So during the linear approach and non-linear approach, we are getting both the times the different output. So that's why we are getting some more idea about like what are the variations we are getting during the different approach like linear and non-linear. We already known about the basic steps related to the import the libraries. So same libraries I can import it over here, and after that we have to import the same thing what we can done in a further all classification techniques. Okay, whenever we are trying to learn any type of the project, or whenever we have to do the at the end of these course we have to try some projects. So at the same time in that project we can explore some more things, because here we have to do some classification, or we have to do some find out some difference between all the techniques. So that's why we have to use same data sets for all the classification techniques, so it should give the better idea like which technique is best for this particular suitable data sets. So first of all we can start with the import the library. Then second step, that is the import the data set. After importing the data set, we have to do some training and testing split, and then we know we have to apply the feature scaling. Now the main part is coming over here when we talk about the fitting support vector machine to the training set. Okay, so till now whenever we have to tested like decision tree as a classifier, so decision tree classifier we have to use random forest classifier, we have to also use the k nearest neighbor, that type of things we have to use. But whenever we are working with the support vector machine, so support vector machine it's a technique, but it is known as the support vector classifier. So that's why from scikit-learn.svm we have to import svc, and after that we are trying to coding with the classifier is equals to svc, it's stand for the support vector classifier. And the main thing is started from over here. First of all we have to see about some linear approach. Okay, so when we want to go with the linear approach, at the same time we are just only simply applied over here the linear. Okay, here, okay, yeah, that is the correct. So we have to just simply apply the kernel is equals to linear and random state is equals to 0. So that's how in a simply manner we have to go from over here, and simple we have to run these things. So we are getting kernel is equals to linear because we have to solve applied over here the
linear approach. In a non-linear, we are also using the polynomial kernel. We are also able to use radial bias function in terms of Gaussian kernel type of things. Okay, but first of all, let's see what type of output we are getting during the linear kernel. That is the main thing is there. After defining these things, now we have to try to define the y prediction as well as. So during the y prediction, we are getting some results based upon y prediction, and at then we are trying to predict the confusion matrix. So let's say in a confusion matrix, we have to see like what type of output we are getting over here. So basically, true positive are 66 are there, and the false negative is 24. So mainly, I just concern with the true positive. Like among the 100 samples, in how many samples it should provide the correct actual output, and it means like we have to define the things like how many times actual output and predicted output should be similar. So 66 times it should happen over here. So similarly, regarding to the linear kernel, now we have to test it the things like what are the graphs we are getting during the training set and testing set. Okay, so this type of like a sigmoid we are getting over here. So whenever at the same time we are getting some type of idea like whenever we are trying to apply the support vector classifier with the linear kernel or the linear approach, we are getting similarly output look like a logistic regression. Okay, in terms of the binary classifier. So this type of output we are getting from training set based upon training set and as well as with the help of the testing setup. So in a both way we are getting the same output. But now the main things we have to see like till now we are still I can only apply the linear approach. Now I want to apply over here the non-linear approach, and that is based upon a Gaussian function. So Gaussian function stand with the RBF. Okay, and when we are going with the RBF at the same time, if you want to provide the value of gamma, so we can also able to provide the value of gamma over here. So let's check it out. Yes, so we are able to over here the value of gamma. So what type of value we have to taken? So whatever the value we can taken like 0.3, that type of value we are also able to taken. I just forgot to take comma. Yeah. Yes. So that is based upon gamma. You can also increase the values of gamma. I just for simply taken, I have to take an RBF. RBF which stand for the radial bias function. It is also known as the Gaussian function. But now we are getting some main idea over here. So here the true positive was 66, but after applying over here the radial bias function, I'm getting the 64 true positive. Okay, so what I can do over here, I'm also able to do these things over here. Like I can increase the gamma. So let's see what type of changes we are getting. No, I was trying to increase the gamma, but still the true positive is 64. But if you can see over here, it should become 26 to 29. So this type of difference should be created whenever you can apply the different approach. Let's check it out the same thing based upon training and testing set visualization. Okay, so when we go with the linear approach, at the same time we are getting some sigmoid type of curve. But when we are trying to apply the RB, if it's a Gaussian or Bell curve, so at the same time we are not getting any type of the sigmoid curve. It's related to the Bell curve is that in part of the training set. As well as if we can check the testing set, so same type of shape we are getting over here in terms of the RBF function with the training set. Sorry, testing set. Similar way, we are also able to provide the polynomial kernel as well as. Let's see how to apply the polynomial kernel. So simply we have to replace the polynomial is equals to kernel, and whenever we are working with the polynomial, at the same time we are also able to take degree over here. So we if we can take a degree, so it should provide the more flexibility. If I currently I have to take degree is equals to 3, so polynomial kernel should work in terms of the degree. That's why. So let's check it out what type of true positive we are getting. Yes, now at the same time we are getting highest true positive with the polynomial kernel, because when we apply the linear approach we are getting 66, but when we apply the RBF kernel we are getting 64 true positive. But when we applied the polynomial kernel at the same time, the true positive should become a 67, and if you can compare with the false negative it should become 19. So it's a very low. In previous one we are getting 26, 29, that type of true negative, the false negative we are getting, but here we are getting less false negative. So that is again important part is there. And also we have to check some output based upon training result. Yes, now it's trying to more fitted over here in terms of the polynomial kernel. The same changes applied over here as well as. But still let's apply the degree is equals to as replacement 3 I have to take on 6 and try to do some more thing over here. Yes, now again it should become 64, and again it should also reflect over here. Yes, so whenever we are trying to change the angle of this one, so it can also affect our accuracy, and true positive and all the parameter based upon a confusion matrix. So that is again based upon a degree. So every degree can provide you the different shape. So that's why let's go with the degree is equals to 5. So we have to get idea like it should provide better thing or not. Okay, it should again provide the true positive is equals to 67. So basically it should become based upon a degree. So let's take a very small degree, like degree is equals to 2. It should provide us the good output or not. Okay, it should provide not good output because the 60 it should become. Yes, it shouldn't be good. Okay, so that's why whenever you are applying a different type of the kernel, and with the kernel, if you can go with the radial bias function kernel, and in that particular kernel, if you can change the value of gamma, so it should also depends upon your output. So that's why during the coding of this type of stuff, so it is very important like in which manner and what the way you are going ahead with this codings. Okay, so basically over here the support vector machine practical should be completed over here, and also this session is also completed over here.